is to calculate the volumes. So just to define what the volume is and to be able to calculate what the volume is. Well, of course, we can't compute volume of everything, but at least we shall be computing volumes of something like parallel epipets, right? So we shall have something like, well, I will better draw it in a skew way, right? So we shall have something like this. Right, so something like a squeezed skew cube, right? And we want to know what the volume is in general dimension. So it's defined by a couple of vectors, this one, and this one. It's called a parallel epipet. This one will be three-dimensional. So of course we know how to do it. We know that it's just taking the first one, then we compute the height of this. So this would be just this length times this length will be the volume of the two-dimensional thing, which corresponds to the fact that we simply can cut it and move this one here, right? And then we have got the same volume, so it's the base, so it's the full length, and then the next one will be projected to the orthogonal component, and so on. And we can just inductively just define it this way, and that's exactly what we shall do. But first we have to imagine that we want to distinguish between viewing the, say, piece of plane from above or from below. So the order of the vectors, so whether this one is the first one and this one the second one, or vice versa, should change the sign. This makes our life much easier. We saw it already in the first weeks, because there I claim, well, you know, so clearly just by defining it by this height, well, basis times height times height, it automatically shows that it's linear in each argument. And if I have as many arguments as the dimension, and I want the thing to be antisymmetric, so changing order of two of the argument should change the sign, then there is just one option up to a scalar multiple, right? So these n-linear antisymmetric things are very rare, so there are not many, just one up to a multiple. And then we look what we want to see for a cube, right? So if you plug in an orthonormal basis, we want to get 1. And this just boils down the option to just one possibility, and that's the volume we get, right? So first we have to deal with something which is called orientation. That will be the orientation of the vector space given by a choice of basis. And of course, from what I told already, it's perhaps clear that each vector space can have only two orientations, and we can distinguish them by telling which bases are the compatible ones with the orientation and which not. And the idea is simple. So we pick up one of the bases. This fixes the orientation, so it's just like fixing the order of the two things for this two-dimensional parallel epipet. And then for any other basis, we look at the transition matrix between the two bases, and either the determinant is positive or negative. If it's positive, it's a compatible one. If it's negative, it's just the other orientation. And that's how we define it, right? So that's the oriented vector space concept. So we simply split the bases, and it's, in principle, it's quite clear if you read through a little bit and think about that there always are exactly two options, and somehow it's splitting the bases into halves, right? So always one of them. If you swap elements of one of the bases, so for each basis you can take any ordering of the elements, and swapping two elements will always change the orientation. And in this sense, you have half of the basis of this one and half of the other one. For a Euclidean space, it means that we have got the Euclidean vector space as its difference space with a fixed orientation. Right, so that's it. Now there is the definition, so we recall the parallel epipets, we talked about that in the last week stuff. And if the parallel epipet is built with linearly dependent U's, it would mean I would just add a third vector here, which would be again in the plane. So then of course I do not, with moving up the height will be 0, and so there will be just the volume of the k-dimensional thing is 0 if the k generators are linearly dependent. But if they are independent, then we simply can iteratively, inductively define how it is. We just simply say that the one-dimensional one is just the length of the U1 is the volume, the one-dimensional volume, and then what we can do is we take the generators which are spanning the parallel epithet in the given order, and we employ the Gram-Schmidt orthogonalization to the U's, right? So we simply look at the Euclidean subspaces always given by the point. So we pick the point here, and first the first one, right? So that's this one. Then we add the second vector, so we get the basement of the skewed cube, and we know that actually instead of the second vector there will be a nice one which will be perpendicular, which will be computed like this by adding some relevant multiple of the first one to the second one to make it orthogonal, and so on. That's the Gram-Schmidt orthogonalization. And then of course we decompose this space as the k-1 spanned bit, and then we take the orthogonal complement in the U1 to UK, right? So we are only in this subspace, and this will be exactly just a one-dimensional thing, and this is how we get it, right? So it will be just the previous one, and that's it. So from that we see that, as I told already, the volume of one-dimensional thing will be this, and the volume of the k-dimensional will be the volume of the k-1 dimensional times ek. And this is the not oriented volume, right? Because here we, in this construction, we didn't take any count about how the things fit with the orientation. So finally what we do is we define the volume either as the plus absolute value if the orientation is compatible, or the minus if it's not. Right? So, well, yes, I should have said that. Right, so that's it, right? So we always just talk about the whole space, the n-dimensional space, which has to be oriented, and then the volume is given with respect to the generators as we want. Of course, if we take a say plane in R3, so you can see that there will be and we fix the orientation of the ambient R3, then there will be a preferred orientation of the plane which is inherited, right? We shall come to that a bit later. So for now we assume that simply we have got the orientation of the n-dimensional subspace, and for that one we can work with this safely. Right, and now the theorem. Well, of course, we knew from the very beginning that the volume had to be this, right? So it's the determinant computed from the coordinates. So we take a orthonormal basis as usual, and we take the coordinates of the individual generators, the U1 through UK. So this is the orthonormal basis of the difference space of the subspace generated by the generators of the parallel epipet, right? And so this is just the fact that the determinant is the only one up to a scalar multiple, which could be something which is n-linear and, or k-linear in our case, and antisymmetric, and therefore it must be that, right? So these MIDs, these vertical bars, do not mean absolute value, they mean determinant now. Sorry, I didn't stress this, but that's how we use it. But it's interesting to see also that there is the second point, because if you are interested in the unoriented volume, so we can also say, well, that will be given by its square, and the square is even much nicer, right? Because you see, you can simply take all the scalar products of the couples and get a symmetric matrix like that, and make a determinant of that, and that's a sort of small miracle, because that gives you the square of the previous one. Well, it's actually not a miracle, we shall see why, but it's nice to know. Right, so we have two formulae how to compute the determinant. The first one gives you the volume including the right sign. The second one gives you the absolute value but squared. And the advantage here is with the second one, we do not have to deal with any basis, right? So if you have something just defined in, say, R3 for such a two-dimensional parallel epipet, so you easily just compute the second matrix. With the first matrix, you would have to first find an orthonormal basis of this subspace and then work with that. Much more work. Right, so how does it work? So first of all, here is the description how the matrix is given, and now the explanation why we have to expect this thing which looks as miracle at the first glance is that if I compute the square of the determinant, what happens? So we know, well, actually I owe you a presentation because we skipped the determinants and I always mention them, what are the properties, but you might remember already that there is this Laplace and Cauchy theorem, and the Cauchy theorem says that the determinant of a product is the product of the determinant. So we know that it will be this. And we also know that the transpose has got the same determinant as the original matrix. So we can write it this way and then come back here. And you see this is a positive semi-definite matrix already. And the scalar products are written in coordinates exactly this way, right? So this must be exactly this matrix. So if one holds, and we know it does, because that's something we can argument via the antisymmetry and the n-linearity, then also 2 holds. But here it's proved directly from the definition via the induction. So this is the computing volume part. What's really nice, well, maybe just to remember, if you find the name gram determinant, then it's exactly the matrix which we have here. So you simply take k vectors and you make a matrix writing down the scalar products of all of the couples. And this comes up more frequently, so here we saw it as tool for computing volumes. The really important, and I think, is the corollary, right? Because what does it mean? So for each linear map on a Euclidean space, the determinant of the map doesn't depend on the choice of coordinates. Even you don't have to use any metric for that, right? So it could be any base you choose. So for every linear map we have got the determinant of the map, and the determinant of the map, in view of what we have proved already, is exactly telling what is the ratio by which the mapping is increasing or decreasing the volumes. Right, so of course, if it's n-dimensional space, so it will be the n-dimensional volumes I'm talking about now. So how do we see it? So we see it very easily, because what would be a matrix of the map phi? So you take simply the basis in which you want to write it. You declare the basis to be orthonormal, so that defines you the scalar product we work with, and then simply the image of the unit cube is mapped to some parallel epipet, and the volume is computed, well, as the volume of the matrix, or as the volume just given by the formula via the matrix. So what we get is really how many times it increases the volumes, because the volume of the unit cube is 1, and we get the result, right? And it doesn't depend on so the ratio doesn't depend on which scalar product we use. So that's a very nice thing. So now we come to some related stuff, so what is called usually the either exterior products or outer products and the cross product. So this starts with just reinterpreting what we are doing, right? So we can understand the determinant as something which eats the columns, so n vectors, and produces a scalar, right? If we change the basis from orthonormal to orthonormal, then the transition matrix will have determinant 1, and therefore the volume computed from these vectors couldn't change. Of course, if we change our coordinates in an orthonormal way, an orthogonal way, then it can't. So the number we call often outer product, and it doesn't bring anything new, but it does, because if we change the basis in a different way, then we shall see that the value of the outer product will change by something depending on the determinant of the transition matrix, which will no more be 1. And we shall meet such things, and we shall see that these will be extremely important to understand integration in more variables in the next semester. So just keep it in mind that there is something like exterior or outer product of vectors, and it's linked to the determinants, and the scalar objects obtained in this way are called densities. But why we are mentioning it now is that if we just fix all the arguments except the last one, then what we get is a linear form. And imagine we are now in a Euclidean vector space, so every linear form is the same thing as a vector, right? And so what we can do is we can declare the vector v, which is called the cross product, to be the unique vector which would evaluate via the scalar product, so viewing the vector v as a linear form, the same way as pushing the remaining argument into the outer product, right? So this is how the cross product is defined. In general, all the engineers know it. Why do they know it? Because if you are in R3, then you may imagine you have two vectors like this. So there is some angle, it's not right necessarily, it could be, but it's not necessary. And then what we do is we want to find a vector which will fulfill this, and this will be a vector which is perpendicular. So this will be the first vector, this will be the second vector, and the perpendicular one will be here. and the size of this will be given by the size of this triangle. So it's half of the parallel epipet, right? So it's related to that, and there is the rule of thumb which says that if I take the fingers in the direction of the two vectors, then the cross product will point out in the direction of the thumb. Right. So here it's written in more details, right? And in particular, again, I mean, I owe you perhaps, or you have to read through yourself. There is this Laplace theorem about expansion of determinants with respect to columns or rows. And if we just write the arbitrary vector this way, and the cross product, which is defined by the previous n-1 vectors u as v in coordinates y1 to yn transposed, then we see that the scalar product here just will be this. And on the right hand side we get the determinant expressing the outer product with the w in the last row, right? And if we expand this determinant with respect to the last column, I wanted to say. If we expand the determinant with respect to the last column, so we get exactly the individual components y1 through yn as the things appearing in the formal polynomial expression in x's. Right, and the cross product is very, very nice object used, say, in computer graphics or everywhere else where you want to get something which is perpendicular and under control, because it's always, as you see, it's always perpendicular. It's non-zero if and only if the other n-1 vectors, so the arguments of the cross product, are linearly independent. The length of the cross product is exactly the size of the parallel epipet, and it's done always in such a way that if you add it, it will be a compatible basis of the oriented Euclidean space V, right? So if we just want to get it the other way around, we simply swap the two red vectors here, the arguments of the cross product, and then it would be the same length but the opposite direction. So that's the end of the story. So we can again make a stop here.